Mars has captivated the imagination of scientists and the public alike for decades. As the closest planet to Earth with the most Earth-like conditions, Mars presents a unique opportunity to explore the possibility of life beyond our own planet. But why is Mars so important in this quest for extraterrestrial life? Mars stands out because it shares several key features with Earth, including its day length, seasons, and polar ice caps. These similarities have fueled speculation about the planet's ability to harbor life, either in the distant past or even today. Unlike the gas giants, Mars has a rocky surface, and evidence suggests that it once had liquid water, a crucial ingredient for life as we know it. The discovery of water in Mars' history opens the door to the possibility that life may have once thrived there, or could still exist in microbial form, hiding beneath its surface. Mars's atmosphere and surface provide a fascinating glimpse into the planet's potential to support life, both in the past and possibly even today. The Martian atmosphere is composed primarily of carbon dioxide, with traces of nitrogen, argon, and oxygen. However, it is incredibly thin, about 100 times less dense than Earth's atmosphere. This thin atmosphere results in low atmospheric pressure, making it difficult for liquid water to exist on the surface for long periods. Additionally, the lack of a substantial magnetic field leaves Mars vulnerable to harsh solar radiation, further challenging the potential for life. Despite these harsh conditions, Mars's surface shows compelling evidence that it once hosted liquid water. Numerous missions have discovered ancient river valleys, lake beds, and mineral deposits that only form in the presence of water. For instance, the Mars rovers have found clay minerals and sulfate salts, both of which are indicative of a watery past. Perhaps the most exciting discovery is the detection of recurring slope lineae, dark streaks that appear to be caused by seasonal flows of salty liquid water. These findings suggest that, while Mars is now an arid desert, it may have once had environments capable of supporting life. The presence of water on Mars is crucial because water is essential for life as we know it. The discovery of ancient water-related features indicates that Mars might have had a more hospitable climate billions of years ago, with a thicker atmosphere and stable bodies of water. This raises the possibility that microbial life could have existed on Mars during this period. Today, the search for water on Mars focuses on the planet's polar ice caps and underground reservoirs, where liquid water could still persist in protected environments. If liquid water exists on Mars today, even in small amounts, it could provide a habitat for microbial life. Mars's geological history further enhances its intrigue. The planet's surface is home to some of the solar system's most remarkable geological features, such as Olympus Mons, the tallest volcano, and Valles Marineris, a canyon system that dwarfs Earth's Grand Canyon. These formations hint at a dynamic past where volcanic activity and tectonic movements could have created environments conducive to life. The planet's history of volcanic activity is particularly intriguing because volcanic heat could have provided the energy needed to sustain life beneath the surface, where water might have been shielded from the harsh surface conditions. Additionally, Mars's past magnetic field, now long gone, might have protected early life from solar radiation, allowing it to thrive during the planet's more temperate early history. The exploration of Mars began with a series of pioneering missions, most notably the Viking program in the 1970s. The Viking 1 and 2 landers were the first successful missions to land on Mars and conduct extensive experiments on the Martian soil. These missions were groundbreaking because they carried out the first direct searches for life on another planet. Although the results were inconclusive and did not provide clear evidence of life, they laid the groundwork for future missions by providing valuable data on Mars's surface conditions and its potential to support life. The exploration of Mars took a significant leap forward with the deployment of more advanced rovers such as Curiosity and Perseverance. Curiosity, which landed on Mars in 2012, has been exploring the Gale crater, a site that scientists believe was once home to a large lake. Curiosity's mission has been crucial in identifying ancient environments that could have supported microbial life. The rover has discovered organic molecules and seasonal methane fluctuations, which are tantalizing hints that life could have once existed or might still exist on Mars. Perseverance, which landed on Mars in 2021, represents the next step in the search for life. Its mission focuses on astrobiology, specifically the search for signs of ancient microbial life. Perseverance is exploring the Jezero crater, another site believed to have once contained a lake. The rover is equipped with advanced instruments designed to detect biosignatures or signs of past life in the Martian rocks and soil. One of the most critical aspects of Perseverance's mission is its ability to collect and cache samples of Martian rock and soil. These samples are expected to be returned to Earth in future missions, allowing scientists to analyze them with the full power of Earth's laboratories. Looking ahead, future missions to Mars are poised to take the search for life to new heights. One of the most anticipated missions is the Mars Sample Return Mission, a collaboration between NASA and the European Space Agency, ESA. This mission aims to retrieve the samples collected by Perseverance and bring them back to Earth for detailed analysis. The Mars Sample Return Mission is considered a critical step in determining whether life ever existed on Mars, as it will allow scientists to conduct sophisticated experiments that are not possible with current technology on Mars. In addition to the Mars Sample Return Mission, other proposed missions, such as human exploration of Mars, hold the promise of deepening our understanding of the Red Planet. Human explorers could potentially conduct real-time experiments, make decisions on the fly, and explore areas that are difficult for robots to reach. These future missions will build on the legacy of past and current missions, each one bringing us closer to answering the profound question of whether life exists or ever existed on Mars. The search for life on Mars employs a variety of sophisticated methods, each designed to detect potential biosignatures, indicators that life may have existed or still exists on the planet. One of the primary approaches involves the analysis of organic molecules in the Martian soil and rocks. Organic molecules are the building blocks of life, and their presence on Mars could suggest that the planet once harbored life. Instruments like the Sample Analysis at Mars, SAM, on the Curiosity rover and the Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, instrument on Perseverance, are designed to detect these molecules with high precision. Another critical method is the search for microfossils, the preserved remains of ancient microscopic life forms. Rovers are equipped with cameras and microscopes capable of capturing high-resolution images of Martian rocks to look for structures that resemble those formed by microbial life on Earth. Additionally, the detection of methane in the Martian atmosphere is a significant focus. Methane can be produced by both biological and geological processes, and its presence, particularly if it varies with the seasons, could indicate ongoing microbial activity. Isotopic analysis is also employed to study the ratios of certain elements in Martian materials, which can provide clues about the planet's environmental conditions and whether they could have supported life. For example, variations in carbon isotopes might suggest biological activity, as living organisms tend to prefer lighter isotopes of carbon. The search for life on Mars has been significantly enhanced by new technologies and developments in space exploration. The Perseverance rover, for instance, is equipped with the most advanced suite of scientific instruments ever sent to the Martian surface. One of its key innovations is the ability to drill and collect core samples from Martian rocks and soil, which will be stored for future retrieval by the Mars Sample Return mission. These samples will allow scientists to conduct more detailed analyses on Earth, using equipment far more sophisticated than what can be sent to Mars. In addition, the Mars helicopter Ingenuity, although primarily a technology demonstrator, has opened the door to the potential use of aerial drones in planetary exploration. Future missions could deploy similar drones to access difficult-to-reach areas, such as deep craters or the walls of canyons, where signs of life might be better preserved. Another exciting development is the ExoMars rover, scheduled for future launch, which will carry a drill capable of penetrating up to 2 meters below the Martian surface. This is crucial because any existing life on Mars is more likely to be found underground, where it would be shielded from the harsh surface radiation. Moreover, advances in remote sensing technology have improved our ability to detect subtle chemical and mineralogical signs of life from orbit. Instruments like the Trace Gas Orbiter, TGO, part of the ExoMars mission, are already analyzing the Martian atmosphere for trace gases that could indicate biological or geological processes. These technological advancements are not only improving our chances of finding life on Mars, but also setting the stage for future missions to explore even more challenging environments, both on Mars and other bodies in our solar system. As we continue to develop and refine these methods, the likelihood of discovering signs of life on Mars increases, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe?